In this video, we will be discussing linear regression. Given 2 points, we know from algebra that we can find a line of the form y equals mx plus b which passes through both of these points. If we are given 3 or more points, there may not be a single line which passes through all of these points. What linear regression tries to do is to find a line which is in some sense a best fit for these points. Consider the following graph. This is a possible line of best fit for the points given in this graph. There are other possible lines of best fit depending on how we might define a line of best fit. What we're trying to do is to find a line that passes as close as possible to all of these points, but not just in terms of immediate distance. If we were minimizing the immediate distance, these red lines would be the distances we would try to minimize. Instead, we're going to try to minimize the vertical distance between the point and the line. And here's why. We're going to use the line to make predictions. Given a data set of points with x's and y's, we're going to try to create an equation that, given an x, will predict the value of y. Recall that we can write the equation of a line as y equals mx plus b. So what we want to do is we would like to find the slope and y-intercept, m and b, for the line of best fit given a set of data points. Here's the formula for the slope of the line of best fit. Given a set of data, x1, y1, x2, y2, up to xn, yn, so we have n data points, the slope of the line of best fit can be found as follows, and here are 2 formulas. Now the first formula is fairly straightforward. We're going to take the deviations of the x's times the deviations of the associated y's and add them all up. And then we'll divide that by the sum of the square deviations of the x-coordinates. Once we find the slope of the line of best fit, then the y-intercept b is equal to the mean of the y's minus the m we just found times the mean of the x's. Let's look at an example of this. Suppose we have the following data set, where x is the time in days and y is the cost in thousands of dollars. Our first data point is 1, 3. Second data point 2, 7. Third data point 3, 13. Fourth data point 4, 16. Next to this, you can see a graph of those data points. We'd like to find the line of best fit. If you add up all of the x's, you'll see that the sum of the x's is 10, and the sum of the y's is 39. If we wanted to use the first formula for the slope of the line of best fit, we would now need to find the x deviations and y deviations from their respective means. Now, x bar, the mean of the x's, that's 10 over 4, the sum of the x's over n, and y bar equals 39 over 4. So then according to our formula, m equals, I need to take the sum of the product of all of the deviations. So for example, x1 minus x bar times y1 minus y bar plus, now we do it for the second data point, x2 minus x bar times y2 minus y bar, etc. And then we would have to divide it by the sum of the square deviations of the x's. So 1 minus 10/4 squared, the first x deviation squared, plus 2 minus 10/4 squared, plus 3 minus 10/4 squared, plus 4 minus 10/4 squared. And we could work this out to find the slope. It turns out that oftentimes this version of the formula for the slope of the line of best fit is not the best one to use. Notice we have a lot of fractions we're dealing with. And even when you're using a calculator to do this, this can introduce a little bit of rounding error. Turns out the second formulation is often the better formulation to use, so let's try to use that formulation. Notice that we need to know the sum of the x's. Well, we've already figured that out. The sum of the y's. We've already figured that out. You need to take the sum of the x's and square them. Well, if we know the sum of the x's, squaring them is easy. We need to find the sum of the x squareds, so that's some work we'll have to do. And we need to find the sum of the x's times the y's. The following table gives us all of this information. We listed out our x's and we added them up, so we have the sum of the x's. We listed out our y's and we added them up, the sum of the y's. We squared each of the x values and we added them up, the sum of the x squareds. We multiplied the x's times the y's, coordinate y's, and added those up, the sum of the x y's. So now our slope can be found by using the formula. M equals n, the number of data points, 4, times the sum of the x y's, 120, minus the sum of the x's, which was 10, times the sum of the y's, which was 39, over n, 4, times the sum of the x squareds, which was 30, minus the sum of the x's, which was 10, squared. Notice that this is a lot easier to calculate on your calculator than the previous version of the formula. And if you work this out, you'll find the slope is 4.5. So now we need to find the y-intercept. Our formula says that b is equal to the mean of the y values, and even if we had not computed that previously, we can find the mean easily using our table on the left. The sum of the y's is 39 divided by the 4 data points. So the mean of the y's minus m times the mean of the x's. And x bar is the sum of the x's over n. And if you work this out on your calculator, you'll see that b is equal to negative 1.5. So the line of best fit for this data set is y equals 4.5 times x minus 1.5. Here's our data set again with the line of best fit graphed on the plot. Now we can make predictions. Remember that x was days and y was cost in thousands of dollars. So we know if the project takes 2 days or 3 days or 4 days, the cost in thousands of dollars. But what if it takes 3.5 days? What would we predict the cost to be in thousands of dollars? Well, using our line of best fit, we have y equals 4.5 times 3.5, the value we're trying to predict, 4, minus 1.5. And if you work this out in your calculator, you'll see that we predict that the cost will be $14.25 thousand. We could also ask the question, when will y equal 15? So we can plug in 15 for y. That equals 4.5x minus 1.5. And if you solve this equation for x, you'll see that x is approximately equal to 3.67. Based on the graph of the line over the plotted points, it looks like this line of best fit really does fit well to this data set. But we would like a formal method to decide if a line of best fit really is a good fit for a set of data. Some data is not going to fit very well on a line. For example, data produced by a quadratic equation. To decide whether or not a data set follows a linear trend, we compute something called the coefficient of linear correlation, given by this formula. When the absolute value of r is close to 1, we say that the data set exhibits a strong linear relation. When the absolute value of r is close to 0, we say that the data set does not exhibit a linear relationship. The table from our previous example had almost all the information we needed to use this formula. The only thing it was missing was the sum of the y squareds, which is integral to this new formula. So if we add the sum of the y squareds to our table, we have all the information we need to find r. In this example, r is equal to n, 4, times the sum of the xy's, 120, minus the sum of the x's, 10, times the sum of the y's, 39, all over the square root of n, 4, times the sum of the x squareds, which is 30, minus the sum of the x's squared. The sum of the x's is 10, and we need to square that, times the square root of n, 4, times the sum of the y squareds, 483, minus the sum of the y's, 39, squared. And if you work this out on your calculator, you'll see that the coefficient of linear correlation for our data set is approximately equal to 0.99267. So we would say that this is a good fit, that this data set does exhibit a strong linear trend, or a strong linear relationship. In practice, by r close to 1, many people consider an absolute value of an r value greater than or equal to 0.8 as being a strong linear trend. If your absolute value of your coefficient of linear correlation is less than 0.8, oftentimes we say that the predictions are unreliable. There is one more thing we need to consider. Consider the following data set and the line of best fit which has been fitted to this data set. Just looking at the graph, we would say that this has a strong linear relationship. In fact, if we computed the coefficient of linear correlation, we would find that it is very close to 1. Now, for predictions made within the range of values exhibited by the data, for example, in these x ranges and in the y values between here and here, these predictions would most likely be fairly accurate. But outside of these ranges, we could be taking a chance. Here is that same graph with the original 4 points marked in red. But notice that if you look at a small portion of even this set of data points, which comes from an exponential function, they might look linear. But if you make predictions outside of the range of original data, your predictions could be very far off. For example, if I wanted to predict the y value at x equals 4, according to my line of best fit, it looks like it's approximately 14. But if we actually look at the data set, it looks like if we follow this exponential trend, it's really someplace up here, much greater than 14. So our approximation would be very far off from the actual value. So you need to be careful about using a line of best fit to approximate data outside of the original data set. Oftentimes, the context of the model or the data set will let you know whether or not a linear trend is an appropriate assumption for the data set. For example, if you were modeling a population model, most likely a line of best fit is not going to be your best bet, because we know that populations tend to grow exponentially. So even if the data seems to have a linear trend, we're probably just looking at a small portion of the data.